Greetings, Astronomy 10, and welcome to your first True Blue lecture of the semester. I wanted to start by telling you why it is exactly that we don't start with Chapter 1 of your textbook. And that's mostly because there's an entire section on reading graphs and some other things that are sort of unnecessary. It's probably good for you to understand what the principle of Occam's razor is, and that, of course, is that if there is a single solution that ties everything up nicely, that it makes a lot of logical sense. All things being equal, the simplest and most complete solution is most often the correct one. That is the philosophical principle of Occam's razor. So that's a good thing to know, just because you're going to hear that a lot in other avenues of life as well, as in science. However, if you are not familiar with the scientific method, and how it is that we go about trying to question the universe and learn things and try to discern the laws of physics and how things work in astronomy and all that good stuff, then it's worth reading the section in the book about the scientific method. It's not bad. Also, if you're not familiar with scientific notation, or with the basic units that we use in science, it might be worth it for you to look over the Working It Out exercise entitled Units and Scientific Notation in Chapter 1. Suffice to say that in science, we don't use pounds, or feet, or yards, or miles, okay? All of that imperial system stuff is goofy and totally irrelevant. So, like most of the world, most of the civilized world, we are going to use the metric system. For smaller measurements, and then for much larger measurements, of course, we're going to use some other standard units that we only pretty much use in astronomy, things like astronomical units and light years and so on. But to begin today's lecture, let me ask you a very simple question, or a question that at first seems simple. How big is the universe? Now, you probably remember a little bit from our first class meeting, a little bit about our cosmic address and where we are in the universe in regards to the rest of the universe and where all the rest of it is. And the further the way that we went from where we are now, the larger the universe appears. And of course there is a sort of a maximum to that. But it may not be exactly what you think. Everybody say hi to Ninja. He's running around inspecting our textbook for us. In any case, if we start from our cosmic address, we started at Evergreen Valley College in the city of San Jose, in the state of California, on the continent of North America, on the surface of Earth, right? In the northern hemisphere, in the western hemisphere, etc. How big is the Earth? Now, I don't expect anyone to have that memorized. That's probably a little too much to ask, especially if you're going to try to figure out what the radius of the Earth is in kilometers or in meters, right? Instead of miles. Suffice to say that the radius of the Earth, and the Earth's not actually a perfect sphere, but the average radius of the Earth is something like 6,400 kilometers. Okay, so that's how big the Earth is. And of course the Earth is, just this tiny little blip, even in comparison to the rest of our solar system. What was our next milestone after the Earth? The next one was the Moon, right? How far is the Moon? Well, the Moon is something like 350,000 kilometers, or 3.5 times 10 to the 8th meters, or 3.5 times 10 to the 5 kilometers, right? For those of us who are already familiar with our scientific notation. So 3.5 times 10 to the 8th just means you move the decimal point over 8 times to get 3.5 from 350 million meters, or 350,000 kilometers. Now, this is where things start to get interesting. How far is it to the Moon? About 350,000 kilometers? on the average? How long does it take light to get there? Now, light moves very fast. It just so happens to be the fastest thing in the entire universe. That was one of the uh, major consequences of Einstein's theory of relativity, is that not only is light the fastest thing in the universe, it is also frame invariant. It always appears to be going at 3 times 10 to the 8th meters per second, regardless of how fast you were going. You could be going in the same direction as the light, the opposite direction of light. You could be moving half as fast as the speed of light, 1.5 times 10 to the 8th meters per second. If you turn on a flashlight, it's still going to look like the light is moving away from you at 3 times 10 to the 8th meters per second, even if you're moving at half the speed of light. Interesting stuff. We'll come back to relativity a little bit later on in the semester. It'll become more important when we talk about redshifts around the edge of the visible universe and so on. But suffice to say that nothing moves faster than light. It is the ultimate speed limit in the universe. It moves at 3 times 10 to the 8th meters per second. That's real fast, or 300,000 kilometers per second. Now, how far away was the moon? 350,000 kilometers, right? So it takes light just over 1 second to reach the moon from the Earth. We would say then that the distance from the Earth to the moon is just a little bit over 1 light second, or the distance that light travels in 1 second. Okay? See how that works? So a light second. There are, of course, light minutes, light hours, light days, light months, light years, and so on. And that's a really, really common one, is the light year, or the distance that light travels in a year. And if you want to know how far a light year is, you can take 3 times 10 to the 8th meters per second, multiplied by 60 to get a minute, multiply by 60 again to get an hour, multiply by 24 to get a day, and multiply by 365 and a quarter, because, once every 4 years we have a leap year, to get the 1 light year distance. It's far. Okay, 1 light year is real far. Our solar system from end to end is not nearly 1 light year. The distance from us to our next nearest neighbor's star is about 4.3 light years. But I digress. How far is the moon from the Earth? About 1 light second, a little bit more, right? 3 times 10 to the 8th meters, or 3.5 times 10 to the 8th meters, or 350,000 kilometers, however you want to say it. How far is the sun from the Earth? Okay, now the sun is significantly farther from the Earth, or the Earth is significantly farther from the sun, than the moon is from the Earth, right? The sun is about 150 million kilometers. Okay, so that's 5 times, or 1.5 times 10 to the 8 kilometers, or 1.5 times 10 to the 11 meters. Very, very far. How long does it take for light to get here from the sun? About 8 minutes. So the sun is about 8 light minutes from the Earth, or the Earth is about 8 light minutes from the sun. Okay, this distance, this 150 million kilometers, is commonly called an AU, or an astronomical unit. This is the unit that we use to measure the distances from planets to their companion stars and so on. So, there are planets that are closer to the sun than we are, right? Mercury and Venus. We're the 3rd rock from the sun. Earth, Mars is about 1.5 AUs, and then there's an asteroid belt, and then Jupiter, and then Saturn, Uranus, and finally Neptune. Neptune is the furthest planet from the sun, at about 30 astronomical units, 30 AUs. But that is not the end of the solar system. There's a region outside of Neptune's orbit called the Kuiper Belt. And a lot of these objects that live most of the time in the Kuiper Belt, a lot of them come inside Neptune's orbit, like Pluto does. These are what we call TNOs, or trans-Neptunian objects. And basically, most of them are kind of like big balls of ice and dust, like Pluto. And that's one of the major reasons that in 2006, Astronomers the world over decided to demote Pluto from planetary status and make it what we call a dwarf planet or a Kuiper Belt object, trans-Neptunian object, all those things. And that's why they made an episode about it on Rick and Morty. But in any case, the Kuiper Belt goes out to about 100 astronomical units, or about 100 times the size of, or 100 times the distance from the Earth to the Sun, right? That's where all those dwarf planets like Pluto live. Okay, there's a structure outside of that, of course. All of the structures so far have sort of been around in a disk around the Sun, right? All of the orbits of all the planets are like in a flat plane. Not exactly, you know, some have tilted a little more or so, or less than others, but they're more or less all sort of in a plane, in a disk around the Sun, including the Kuiper Belt. But the next region further out from that, that goes out from 100 AUs and further out, is called the Oort cloud. Now the Oort cloud is primarily where objects like comets and such, those all kind of live out there, you know, and they come into the inner solar system sometimes. There's a very famous comet called Halley's Comet that comes around once every 76 years or something like that. But it doesn't go nearly as far. It doesn't really go all the way out, you know, into the Oort cloud. There are some comets that only come anywhere near the inner part of the inner solar system every few thousand years. And that's more typical. Some of them just kind of stay out there the whole time. It's this big sort of spherical cloud-shaped kind of nebulous blob that has over 1 trillion particles in it, some of which are big old comets and some of which are very, very small comets. And that's about the end of our solar system. The solar system really isn't that big, you know, from a few hundred AUs to maybe 1,000, depending on your estimate. And that's not that far. The next nearest star to us is Proxima Centauri. That's the next nearest neighbor star, and is about 4.3 light years from us, meaning that light from Proxima Centauri takes 4.3 years to get here for you to be able to see in your telescope. It takes a long time. And that's nothing, because just in our own galaxy, there are something like 100 billion stars, and from end to end, the Milky Way galaxy is something like 100,000 light years across. Now we are sort of in no special place. We're sort of in between the Orion Arm and sort of the area just immediately outside of it. And that puts us about halfway in between the core and sort of the rim, or the edge of the galaxy. So if we were to try to look at light from the very, very far side, right, at the very edge, at the far edge of the galaxy, it would take light 75,000 years to get from the edge of the galaxy to go all the way through the center to get to us on the other side. And even that's nothing, because our next major nearest galaxy neighbor is the Andromeda Galaxy, which is something like 2.5 million light years from us. Meaning, if you look up in the sky with your telescope and you can see the Andromeda Galaxy with it, actually, the Andromeda Galaxy you can see with your naked eye. It is the object in the universe that is farthest away that you can actually see with your naked eye. It actually looks kind of just like a little smudge. If you've ever gone out and seen the Milky Way, it kind of looks like somebody spilled a bunch of milk across the sky, right? And that's actually where it comes from. That's not only the name comes from that, but indeed the word galaxy comes from galactose, like milk. And in any case, the Andromeda Galaxy looks like a tiny little smudge made out of that milk that makes up the Milky Way. Because the Milky Way is tons and tons of stars, you know, 100 billion of them, right? And so is the Andromeda Galaxy, the thing that looks like a smudge. But in any case, It's about 2.5 million light years from us. So if you look up and see it, the light that is getting to your eye was emitted 2.5 million years ago. We call that look back time. And so if you're looking at the Andromeda galaxy, you're actually not seeing it as it is now, but as it was 2.5 million years ago. Now, 2.5 million years is not really a very long time if you're talking about the lifespan of a star. Our sun is about 5 billion years old, and it will live for another 5 billion years before it eventually becomes a red giant, and then an asymptotic red giant, and then blows up, leaving behind a white dwarf. But we'll talk more about that close to the end of the semester when we talk about the evolution of low-mass main sequence stars. In any case, the Andromeda galaxy isn't that far, right? The Andromeda galaxy is one of a dozen or so galaxies in a cluster we like to call the local group. And that's just our local, tiny little cluster of galaxies. There are actually three sort of large-ish galaxies. The Milky Way and the Andromeda galaxy are the largest of those, but there's also the Triangulum galaxy, which is smaller. But there are several galaxies sort of hovering directly near us. A lot of them we are sort of devouring already, things like the Sagittarius dwarf galaxy. But then there are also a bunch of other ones. Some of them were a little further away, some were closer to Andromeda. But there's something special about this group, the local galactic group, in that the local group is all gravitationally bound. And so at some point in the future, the gravity of all of the stars and everything combined will eventually make the local group all into one large galaxy. That's going to take some time, however. In any case, the local group is just one tiny little dot, one tiny little galaxy group, and a huge cluster of galaxy clusters called the Virgo supercluster. The distance from us to the center of the Virgo supercluster is something like 65 million light years. And even that's nothing. Our next closest supercluster, after our own, the Virgo cluster, is about 300 million light years from us. And we can see tons and tons of superclusters all over the visible part of the universe, up until about 13.7 billion light years in all directions. And of course and we can't see any further than that. We can't see any further back in time than 13.7 billion years, and so we don't have any look-back time or visible distance beyond 13.7 billion light years or so, because light has not traveled farther than that since time began. Now, after the Big Bang, which we're going to talk about again closer to the end of the semester, which, suffice to say, has been more or less proven. There's lots and lots of evidence pointing to the Big Bang. So according to the Big Bang theory, there was a period of unprecedented expansion in the early universe. We call that inflation, kind of what happens to your bank account every year, right? You may accrue like a few dollars in interest, but all of that becomes continually devalued because everything becomes more expensive, right? But not to be confused with that kind of inflation. Shortly after the universe came to be, after the Big Bang, there was a period of expansion where everything expanded much, much faster than it should have. And for that reason, the universe, we think, is actually much larger than a bubble 13.7 billion light years in radius. We think probably the universe is at least 100 billion light years in radius. And so the part that we can see is very small compared to everything else that's out there. Interesting, right? So that's the universe. It is very, very large. And we occupy a very, very small place in it, not a very special place, but kind of in the sticks in the middle of nowhere, in the boonies. And so, what is a good place to try to start to understand the universe around us and where we are? Well, generally, when we're just starting the study of astronomy, what we do is we like to start by showing how we look at the sky, right, and how we figure things out. And so what we're planning on doing, what we usually plan on doing, is we start with our own perspective, what it looks like trying to study the sky from our place here on Earth. And so that requires that we define a few important terms to help get our bearings and try to figure things out, right? Trying to get rid of the lens flare. Sorry, we're just going to have to put up with it for the moment. In any case, so if you're out under the sky, right, if you look up at the sky, if you look up at the point directly above you on the sky, there's a special term for that. Now, this is because these few terms, these next set of terms that I'm going to give you are all relative to you, the observer, okay? And if you were to move somewhere else on the surface of the Earth, all of these things would move with you. They are relevant and defined by your position, okay? Excuse me. So the zenith is the point on the sky directly above you. There's also another thing, another point theoretically in the sky, on the opposite end of the sky, directly below you. And if you were to look straight down through the Earth, to the opposite side of the Earth, to the sky on the other side of the Earth, you would see the nadir, right? Above you, the zenith, below you, the nadir. Okay? There's also your horizon, right? Obviously, you can only see basically half of the view that you can see at most is the sky, right? The other half is the Earth and everything below you. And so the horizon is where the sky meets the Earth, right? They don't actually meet, right? They don't actually collide or anything like that, right? It's just where the sky is no longer blocked by the Earth. That's the horizon, okay? Now, there is a line, an imaginary line, of course, because this is relative to you. There's a line that goes from north to your zenith to south. That's called the celestial meridian. The celestial meridian. Now, if you wanted to try to point out some point on the sky, you can use two coordinates in order to do so. The first of which is what we call the altitude. Directly above you is 90 degrees, at the horizon is 0 degrees. And so if you're talking about a 10-degree altitude, that would be 10 degrees up from the horizon, right? So this angle in between these two would be something like 10 degrees. And then, 10, 20, 30, 40, 50, 60, 70, 80, and then 90 is straight up, okay? Your altitude, right? The altitude of whatever point on the sky you're pointing at. If you wanted to point out a planet or an airplane or whatever, you'd say it's that altitude. Now, that of course isn't sufficient because you could have 10 degrees altitude there and 10 degrees altitude there and 10 degrees altitude there and so on, right? And so we need some direction indicator. We call this one the azimuth. Azimuth. A-Z-I-M-U-T-H. Directly north is 0 degrees azimuth. And then you would go clockwise, increasing from 0 to 90 degrees, at which point you would be pointing directly east. 180 is south, 270 is west, and then as you get all the way up to 359 and back to 0 or 360, that's north. Okay? So you would say something like 30 degrees altitude, 50 degrees azimuth, and so you'd be 50 degrees east of north and 30 degrees up from the ground, and you'd be pointing in exactly that direction. Okay, so you could tell somebody where the moon was or something like that using altitude and azimuth, and you have a sort of common frame of reference. Now that works pretty well if we're in the same place on the Earth. Two people at opposite ends of San Jose, that works pretty well for them. But if you were going to try to point things out using altitude and azimuth coordinates, if one person was at the North Pole and one person was at the South Pole, it wouldn't work so well, right? Why is that? Well, I'm glad you asked. There are two special points on the sky called the celestial poles. If you were standing on the North Geographic Pole, on the North Pole of the Earth, and you were to look straight up, your zenith would be at the North Celestial Pole. Okay? Your nadir then would be the South Celestial Pole. But if you were standing at the South Pole, the Earth's South Geographic Pole, which pole would be at your zenith? The South Celestial Pole, right? And then your nadir would be the North Celestial Pole. So if you're in two different places on the surface of the Earth, altitude and azimuth don't translate so well. But if you're at the same place, you can point things out pretty readily, right? Okay. Now, once upon a time, a long, long time ago, people used to think that all of these stars and distant objects in the sky were affixed to a sphere. And that sphere would rotate around us because, of course, we're the center of the universe, right? This thing was called the celestial sphere. And it is not real. But we sometimes use this model, this construct, this imaginary celestial sphere, because it is a useful tool for understanding how it is that things in the sky move. How can this be? Well, if you imagine for a moment that everything outside of the Earth is stuck to a sphere, right? All of the stars, the sun even, right? Then that would explain why day goes to night and all that, right? If you think about where the sun is when it rises and where it is when it sets, right? The sun rises in the east and it goes across the sky and sets in the west. And then, as the sun sets, stars all do the same thing, right? They go from the east across the sky to the west. So it appears that this entire sphere, this fake construct that goes around the Earth, goes from east to west. Now, why does that happen? Why do stars appear to go one way? Why does it look like the sun rises in the east and sets in the west? It's because the Earth is rotating the opposite direction, right? Makes perfect sense, doesn't it? That's our first piece of evidence against the flat Earth crazies. In any case, obviously stars rise and set because the Earth is rotating in the opposite sense, right? So the sky, the celestial sphere, appears to revolve around us from east to west because the Earth is rotating from west to east, the other way. Okay, I want you to think about the North Star. It's called Polaris. If you can find the Big Dipper, you can find Polaris, right? You just have to start with the handle. You go from the handle and then around the cup, and the last two stars, they call the pointer stars, point up to the North Star. The North Star is kind of not really in a special place. It's not a super bright star, but it is kind of by itself, and it makes it easy to identify. Now, the North Star is very, very close to the North Celestial Pole, right? And so as the celestial sphere rotates, right, as the Earth rotates in space, causing the stars that are, way far away to look like they're moving around on a sphere. If you are in San Jose, and assuming that there's no clouds in the sky, can you look up at any time of the year and see the North Star? Is there any time of the year where you can't see the North Star? Is there any time of day or night when you can't see the North Star? Obviously, during the day, you can't see the North Star because the sky is blue, right? But beyond that, you cannot find a time of the year where here at 38 degrees north latitude, you cannot see the North Star. Why is that? Well, let's think about this here for a second. If we are here on the surface of the Earth, right? Let me find North America. I don't have a globe, so this decanter is going to have to do. So here we are in North America, right? California here on the west coast. So if you're standing here, and this is where the North Star is, right? Above the stopper, right? That's the North Pole. And so the Earth rotates from west to east like this, causing the stars, which are actually fixed, to look like they're moving this way, right? In any case, here we are. And the horizon is essentially from 0 to 90, right? So we can see all this portion of the sky. And because the north celestial pole is going to be way higher in the sky than any mountains or anything, unless maybe you're right next to them, we can see this at every time of the year. Now, of course, if we were standing on the North Pole, the North Star would be like directly above us on the sky, right? And so if you were standing at the North Pole, the North Star would be basically at your zenith. However, if you were at the equator, where is the North Star now? It's at your horizon, right? You may or may not be able to see it so well. If there's even just a little bit of mountains or whatever, yeah, you're toast. You can't see it, right? Now, as we proceed northward, the stopper will tell us the altitude. Remember, distance from zero, angle from zero, right? So here we are at the equator. It's at 0 degrees altitude. If we go up 10 degrees altitude, or if we go up 10 degrees latitude, excuse me, the North Star, the North Celestial Pole, is going to be at 10 degrees altitude. And then if we get up here to where we are in San Jose at about 38 degrees north latitude, the North Celestial Pole and the North Star should be about 38 degrees up from the horizon until, we move further and further north and finally get to the North Pole where it's at 90 degrees. Long story short, your latitude, or your angular distance from the equator, will also tell you the altitude of the North Star. Okay? Now, that means here, at any time of day or night, the North Star does not set. We call that circumpolar, Circumpolar. And as a matter of fact, there's a circle of stars that's about 38 degrees that never set, right? Think if you were at the equator and the Earth just kind of rotated like this. All of the stars in the sky would rise in the east and set in the west at different times of the year, of course. And so there would be no such thing as a circumpolar star if you're standing exactly at the equator. But if you're standing at the North Pole, then the Earth rotates like this, and all of the stars in the sky just kind of appear to move around you. Now, for the 6 months of the year, because the Earth is actually tilted like this on its axis, right? it's 23.5 degrees sort of pointed. In the summer, the northern hemisphere is pointed towards the sun, and in the winter, the southern hemisphere is pointed toward the sun. And this is why we have seasons, but we'll talk a little bit more about that during our next lecture. In any case, a little bit of smudge. I have to clean this up later. In any case, if you're standing here at the equator, no stars are circumpolar. But if you're standing here at the North Pole, all stars are circumpolar, right? Nothing rises or sets, it just kind of moves around you. And if you were there for the 6 months of the year where it's dark, right, when we have winter in the northern hemisphere, if you're at the North Pole, you don't see any sun for about 6 months. And so you can just kind of see all the stars whirling around you as day turns to night, turns to day, even though the sun isn't rising, right? Every 24 hours, the stars will go all the way around you. And the same is true at the south celestial pole, except that that happens when we have summer in the northern hemisphere, when you have winter in the southern hemisphere. But we'll talk more about seasons next time. In any case, I want to talk to you just a little bit really briefly about how to read a star chart. So we use altitude and azimuth to try to find a point on the sky relative to where we are. We would use two other coordinates called right ascension and declination to try to find where things are on the sky in total, right? Now, the way that that works is the sky is divided up east to west into 24 hours of right ascension. And the theory behind that is that a particular object will be right ascended, right, or at its highest point in the sky, the equidistant from east and west, right, equidistant from the horizons, the highest point in the sky, at a certain hour or a certain time of day or night, right? And so if you look at a star map that has the right ascension on the bottom in hours, you can get a sense of what time these should rise. And of course, you're only going to be able to see certain stars at certain times of day, you know, in different places on the Earth, right? But we'll talk a little bit more about that next time. Also, the declination, that's like latitude, but on a star map. Now, star maps are kind of a funny thing. If you ever pick up a star map, most likely they probably will have right ascension and declination noted on them. If they don't, or sometimes even if they do, they're also labeled north, south, east, west, so you know where to look when you pick the map up. But there's something very interesting and subtle, a little bit different from the other maps that you've probably ever looked at in your life. So go ahead and have a look at the image of the July stars from, I believe these are from the northern hemisphere. Now what's different about that? There's one thing you may have noticed is that two of the major cardinal directions, the east and west, are reversed. And the reason for that is a little bit subtle. You read a map like this, right, north, south, east, and west, but you would read a star map like this holding it up to the sky. And so you would either have to reverse the north and south or the east and west, right, in order to align it properly to do so. All right, that concludes your first major lecture. Be sure to ask any questions, if you have any, so you are prepared for the quiz next time. I hope you've enjoyed this lecture as much as I have had giving it.